Tonight, we're exploring one of the most important concepts for understanding life in the universe: the Goldilocks zone. You've probably heard this term before, maybe in a documentary or science class. But here's what most people don't realize. Earth sits in a narrow band around the sun where conditions are just right for liquid water to exist on the surface. Not too hot, not too cold, just right. Move us a bit closer to the sun and we'd be Venus, a hellscape with surface temperatures hot enough to melt lead. Move us farther out and we'd be Mars, a frozen desert where water can't stay liquid on the surface. The Goldilocks zone is why we exist. It's why life developed on Earth and not on every planet. And the remarkable thing, this zone is incredibly narrow. We're talking about a range that's only a small percentage of the total distance from the Sun to the outer solar system. We won the cosmic lottery just by being in the right place. So how did Earth end up in this perfect spot? What makes the Goldilocks zone so special? And are there other planets around other stars sitting in their own habitable zones right now? If you want to understand why Earth is special, why life exists here, and what we're looking for when we search for life beyond our solar system, then subscribe, because we're diving deep into the science that makes our world possible. Now, let's begin. The term Goldilocks zone comes from the fairy tale about Goldilocks and the three bears. You remember the story? Goldilocks enters the bear's house and tries 3 bowls of porridge. One is too hot, one is too cold, and one is just right. The same principle applies to planetary habitability. There's a zone around every star where the temperature is just right for liquid water to exist on a planet's surface. Not too hot where water boils away. Not too cold where it freezes solid. Just right for liquid water. And liquid water, as far as we know, is absolutely essential for life. Why is liquid water so important? Because life as we understand it requires a solvent, a liquid medium where complex chemistry can happen. Water is an incredible solvent. It dissolves more substances than almost any other liquid. It allows molecules to move around, interact, and form the complex chemical reactions that underlie biology. Water also has unusual properties that make it perfect for life. It's densest as a liquid, not as a solid, which means ice floats. This is rare. Most substances are densest in their solid form, but water expands when it freezes. This matters enormously because it means ice forms on top of bodies of water rather than sinking to the bottom. Lakes and oceans freeze from the top down, creating an insulating layer of ice that protects liquid water underneath. Life can survive in that liquid water even when the surface is frozen. Water also has a high heat capacity, meaning it takes a lot of energy to change its temperature. This helps regulate climate. Oceans absorb heat during the day and release it at night, moderating temperature swings. Water is transparent to visible light, but absorbs infrared, which helps create the greenhouse effect that keeps Earth warm. Water molecules are polar, meaning they have a slight positive charge on one end and a slight negative charge on the other. This polarity allows water to dissolve ionic compounds and interact with other polar molecules, making it perfect for the chemistry of life. So, when we talk about the Goldilocks zone, we're really talking about the range of distances from a star where liquid water can exist on a planet's surface. Not water vapor in the atmosphere, not ice frozen on the ground. Liquid water stable over long periods of time, forming oceans or lakes or rivers where complex chemistry can occur. This is what we mean by habitable. It doesn't mean life definitely exists there. It means conditions could potentially support life as we know it. Now, let's be clear about what determines whether water stays liquid. Temperature. If it's too hot, water boils and becomes vapor. If it's too cold, water freezes and becomes ice. And temperature on a planet's surface is primarily determined by how much energy it receives from its star. Planets receive energy in the form of radiation, mostly visible and infrared light from their star. The amount of radiation a planet receives depends on two main factors: how luminous the star is, how much energy it's putting out, and how far the planet is from that star. The relationship between distance and radiation follows the inverse square law. This is crucial to understand. As you move away from a source of radiation, the energy spreads out over a larger area. Specifically, if you double the distance, the radiation is spread over 4 times the area, so each square meter receives 1/4 as much energy. Triple the distance, and you get 1/9 the energy. The energy decreases with the square of the distance. This is why distance matters so much. A small change in distance from the star can mean a big change in how much energy a planet receives. Let's make this concrete with numbers. The sun puts out a certain amount of energy, what we call its luminosity. Earth sits at an average distance of about 150 million kilometers from the sun. At this distance, Earth receives about 1,360 watts of solar energy per square meter facing the sun. This is called the solar constant. Now, Venus is about 108 million kilometers from the sun, closer than Earth. Because it's closer, it receives more solar energy per square meter, about 2,600 watts, nearly twice as much. Mars is about 228 million kilometers from the sun, farther than Earth. It receives only about 590 watts per square meter, less than half what Earth gets. These differences might not sound dramatic, but they have enormous effects. The amount of energy a planet receives determines its equilibrium temperature, the temperature it would have based purely on the balance between incoming solar radiation and outgoing thermal radiation. For Earth, if we had no atmosphere, the equilibrium temperature would be about -18 degrees Celsius, well below freezing. But Earth's atmosphere, particularly greenhouse gases like carbon dioxide and water vapor, trap some of the outgoing thermal radiation and warm the surface. This greenhouse effect raises Earth's average surface temperature to about 15 degrees Celsius, comfortably above freezing. This is why we have liquid water oceans covering 70% of the planet's surface. Now, let's visit the planets that are outside the Goldilocks zone and see what happens when you're too close or too far from the Sun. We'll start with Mercury and Venus, the two planets closer to the Sun than Earth. Mercury is the innermost planet, orbiting at an average distance of about 58 million kilometers from the Sun. It receives about 9 times more solar radiation per square meter than Earth does. You might expect Mercury to be incredibly hot, and parts of it are. The side facing the Sun can reach temperatures of about 430 degrees Celsius, hot enough to melt lead. But here's something interesting. Mercury is not in the Goldilocks zone, but not just because it's too hot. Mercury has almost no atmosphere. Whatever gases existed when Mercury formed have long since been stripped away by the solar wind and Mercury's weak gravity. Without an atmosphere to trap and redistribute heat, Mercury has no greenhouse effect. The side facing away from the Sun gets incredibly cold, dropping to about minus 180 degrees Celsius at night. This extreme temperature difference between day and night is one reason Mercury couldn't support life as we know it. But the bigger issue is that even on the cooler night side, the lack of atmosphere means no liquid water. Water would either boil away on the hot side or freeze solid on the cold side. There's no stable region where it could remain liquid. Mercury also rotates very slowly once every 59 Earth days, which creates these extreme temperature variations, and it has no magnetic field strong enough to protect any hypothetical atmosphere from being stripped away by the solar wind. Mercury is a dead world, airless, waterless, lifeless. Venus is more interesting and more tragic. Venus is nearly Earth's twin in size and mass. It's about 95% Earth's diameter and 80% Earth's mass. It orbits at 108 million kilometers from the Sun, about 72% of Earth's distance. It receives nearly twice the solar energy Earth does. You might think this would make Venus warm, but not unbearably so. Maybe temperatures like a hot desert on Earth. But Venus is nothing like that. Venus is a hellscape. Its surface temperature is about 467 degrees Celsius. That's hotter than Mercury's day side, even though Venus is farther from the Sun. How is this possible? The answer is Venus's atmosphere. Venus has an incredibly thick atmosphere, about 90 times the pressure of Earth's atmosphere at sea level. That's equivalent to the pressure you'd experience a kilometer underwater in Earth's oceans. And this atmosphere is 96% carbon dioxide, a powerful greenhouse gas. The greenhouse effect on Venus is extreme. Solar radiation passes through the atmosphere and heats the surface. The surface radiates thermal energy back as infrared radiation, but the thick carbon dioxide atmosphere absorbs that infrared radiation and re-emits it in all directions, including back down toward the surface. This trapped energy builds up, heating the surface to extreme temperatures. Venus wasn't always like this. Scientists think Venus might have had liquid water oceans early in its history, perhaps for the first 2 billion years after it formed. But being closer to the Sun meant it received more solar energy than Earth. This caused more water to evaporate into the atmosphere. Water vapor is itself a greenhouse gas. More water vapor in the atmosphere meant more greenhouse warming. This caused even more water to evaporate. This is a runaway greenhouse effect. Once started, it feeds on itself. Eventually, the oceans evaporated completely. The water vapor in the atmosphere was broken apart by ultraviolet light from the Sun. The hydrogen escaped to space because hydrogen is very light and Venus's gravity couldn't hold it. The oxygen reacted with rocks on the surface. With no water left to absorb carbon dioxide, volcanic activity kept adding more and more carbon dioxide to the atmosphere. Carbon dioxide built up to enormous concentrations because there was no mechanism to remove it. On Earth, carbon dioxide dissolves in ocean water and eventually gets locked into rocks through various chemical processes. Venus lost this carbon sink when it lost its oceans. The result is the thick carbon dioxide atmosphere we see today and the extreme surface temperatures. Venus is a cautionary tale about greenhouse warming gone out of control. Venus is also outside the Goldilocks zone, though barely. Some definitions of the inner edge of the habitable zone place it right around Venus's orbit or slightly inside it. But the key point is that even if Venus is technically at the edge of the zone, its thick carbon dioxide atmosphere has pushed it far beyond habitable conditions. This teaches us something important. Being in the Goldilocks zone is necessary but not sufficient for habitability. A planet's atmosphere matters enormously. You can be in the right zone distance-wise and still end up uninhabitable if your atmosphere creates too much greenhouse warming. Now, let's travel outward past Earth to Mars. Mars orbits at about 228 million kilometers from the Sun, about 1.5 times Earth's distance. It receives less than half the solar energy Earth does. Mars is also much smaller than Earth, about half Earth's diameter and only about 11% Earth's mass. This matters because smaller planets have weaker gravity and cool faster after formation. Mars has a very thin atmosphere, only about 1% of Earth's atmospheric pressure at the surface. This thin atmosphere provides almost no greenhouse warming. Without a substantial greenhouse effect, Mars is cold. Its average surface temperature is about -63 degrees Celsius. It can get as warm as about 20 degrees Celsius at the equator during summer days. But nighttime temperatures plummet to -100 degrees Celsius or colder. Water exists on Mars, but not as liquid on the surface. Mars has polar ice caps made of water ice and carbon dioxide ice. There's water ice in the soil at high latitudes. There might be substantial amounts of water ice in the subsurface across much of the planet, but liquid water is unstable on the surface because of the low temperature and low atmospheric pressure. At Mars's atmospheric pressure, water sublimates, going directly from ice to vapor without passing through a liquid phase. Or if liquid water somehow appeared on the surface, it would quickly freeze or evaporate depending on the temperature. But here's something fascinating. Mars wasn't always like this. We have strong evidence that Mars once had liquid water on its surface in large quantities. The surface is covered with features that look exactly like dried river valleys, ancient lake beds, and even an ancient ocean basin in the northern lowlands. Some of these features are billions of years old. This means early Mars must have been warmer and had a thicker atmosphere with enough greenhouse warming to keep water liquid on the surface, despite receiving less solar energy than Earth. What happened? Why did Mars lose its water and become the cold, dry desert we see today? The answer is connected to Mars's small size. Because Mars is small, it cooled faster after formation. The interior solidified relatively quickly. This shut down the dynamo that generated Mars's magnetic field. Earth maintains a magnetic field because our interior is still partially molten and we have convection in the outer core, liquid iron moving and generating magnetic fields. Mars had this too early in its history, but lost it as the planet cooled. Without a magnetic field, Mars became vulnerable to the solar wind. The solar wind is a stream of charged particles flowing out from the Sun in all directions. Earth's magnetic field deflects these particles, protecting our atmosphere. Mars, without a protective magnetic field, had its atmosphere slowly stripped away by the solar wind over hundreds of millions of years. As the atmosphere thinned, greenhouse warming decreased. Surface water froze or evaporated and was lost to space. Mars transitioned from a potentially habitable world with rivers and lakes to the cold, dry planet we see today. Mars is outside the Goldilocks zone, too far from the Sun to maintain liquid water on its surface with its current thin atmosphere. But it might be near the outer edge of the zone. If Mars had kept its thick atmosphere and magnetic field, it might have remained habitable despite the lower solar energy input. This teaches us another crucial lesson. Being in the Goldilocks zone depends not just on distance from the star, but on the planet maintaining the right atmospheric conditions over billions of years. Small planets might not be able to do this even if they start out in the habitable zone. So, we've seen what happens when you're too close like Venus and what happens when you're too far like Mars. Now, let's talk about Earth, the planet that's just right. Earth orbits at 150 million kilometers from the Sun, receiving 1,360 watts per square meter of solar radiation. With our atmosphere providing greenhouse warming, our average surface temperature is about 15 degrees Celsius. This keeps water liquid across most of the planet's surface. We have oceans covering 70% of the surface, lakes, rivers, and water vapor in the atmosphere. Water exists in all three phases: solid ice at the poles and in glaciers, liquid water in oceans and lakes, and water vapor in the atmosphere. But it's the liquid phase that's dominant and that makes Earth habitable. Earth's atmosphere is about 78% nitrogen and 21% oxygen with trace amounts of other gases including water vapor and carbon dioxide. The carbon dioxide concentration is currently about 0.04%, though this is increasing due to human activities. This small amount of carbon dioxide, along with water vapor and other greenhouse gases, provides enough greenhouse warming to keep Earth comfortable. Not too much like Venus, not too little like Mars. Just right. But Earth's habitability isn't just about distance and atmosphere. Many other factors contribute to making Earth the perfect place for life. Earth has a strong magnetic field generated by convection in our liquid outer core. This magnetic field extends far into space, creating the magnetosphere that deflects most of the solar wind. Without this protection, our atmosphere might have been stripped away over time like Mars's atmosphere. The magnetic field is one reason Earth has been able to maintain its atmosphere for billions of years. Earth also has plate tectonics. Our crust is broken into large plates that move slowly over the mantle. Plates collide, creating mountains. Plates separate, creating rift valleys and new crust. This constant recycling of crust is important for regulating Earth's climate over geological timescales. When rocks are exposed at the surface through mountain building, they weather and react with carbon dioxide from the atmosphere. This carbon dioxide gets carried to the oceans by rivers, eventually forming carbonate rocks on the ocean floor. These rocks get subducted, pulled back into the mantle at plate boundaries. Some of this carbon dioxide is released back to the atmosphere through volcanic activity. This cycle, driven by plate tectonics, acts as a thermostat for Earth's climate. If the planet gets too hot, more weathering happens, removing carbon dioxide from the atmosphere, reducing greenhouse warming, cooling the planet. If the planet gets too cold, less weathering happens. Volcanic activity continues adding carbon dioxide, increasing greenhouse warming, warming the planet. This geological carbon cycle has helped keep Earth's climate relatively stable over billions of years, despite the sun's luminosity gradually increasing. When the sun first formed, it was about 70% as bright as it is today. With less solar energy, you might expect early Earth to have been frozen. But evidence shows liquid water existed on Earth's surface as far back as about 4 billion years ago. The explanation is that Earth's atmosphere had more greenhouse gases back then, particularly carbon dioxide, which compensated for the dimmer sun. As the sun gradually brightened over billions of years, the geological carbon cycle gradually removed carbon dioxide from the atmosphere, preventing Earth from overheating. This is one reason Earth has maintained habitable conditions for so long. Earth also has a large moon relative to its size. The moon is about 1/4 Earth's diameter, much larger relative to the planet than most moons in the solar system. The moon's gravitational pull creates tides in Earth's oceans and even slight deformations in the solid Earth. These tides transfer angular momentum from Earth's rotation to the moon's orbit. This is gradually slowing Earth's rotation, making days longer and pushing the moon farther away. Early in Earth's history, days were much shorter, maybe only 6 hours long. The moon was much closer. Over billions of years, Earth's rotation has slowed to its current 24-hour day, and the moon has moved out to its current distance of about 384,000 kilometers. The moon also stabilizes Earth's axial tilt. Earth's rotation axis is tilted about 23.5 degrees relative to its orbital plane. This tilt is what creates our seasons. Different parts of Earth receive more direct sunlight at different times of year as Earth orbits the sun. Without the moon's gravitational influence, Earth's axial tilt would vary chaotically over millions of years due to gravitational perturbations from other planets, particularly Jupiter. This varying tilt would create wild swings in climate. But the moon's presence stabilizes the tilt, keeping it within a fairly narrow range. This stability has allowed complex life to evolve without facing catastrophic climate changes caused by shifting axial tilt. So Earth's habitability comes from many factors working together. The right distance from the sun to receive the right amount of solar energy, an atmosphere with just enough greenhouse gases to maintain comfortable temperatures, a strong magnetic field protecting the atmosphere from being stripped away, plate tectonics regulating the climate through the geological carbon cycle, a large moon stabilizing our axial tilt and creating tides. All of these factors combine to make Earth not just habitable, but stable in its habitability over billions of years. This is what allowed life not just to start, but to persist and evolve into the incredible diversity we see today. The traditional definition of the Goldilocks zone focuses on distance from the star and the amount of energy a planet receives. For the Sun, the habitable zone is estimated to extend from about 0.95 AU to about 1.37 AU. An AU, or astronomical unit, is Earth's average distance from the Sun, about 150 million kilometers. So, the inner edge of the habitable zone is about 143 million kilometers from the Sun, slightly inside Earth's orbit. The outer edge is about 206 million kilometers between the orbits of Earth and Mars. This is the range where a planet with an Earth-like atmosphere could maintain liquid water on its surface. Venus at 0.72 AU is inside the inner edge. Mars at 1.52 AU is just outside the outer edge. Earth at 1.00 AU is comfortably in the middle. We're in the sweet spot. But remember, these boundaries are not sharp. They're estimates that depend on assumptions about planetary atmosphere, greenhouse effect, and other factors. A planet just inside the inner edge might still be habitable with the right atmosphere. A planet just outside the outer edge might be habitable if it has a thick enough atmosphere to provide sufficient greenhouse warming. The Goldilocks zone is more like a fuzzy band than a precise boundary. Also, the Goldilocks zone changes over time as stars evolve. The Sun is gradually getting brighter as it ages. This means the habitable zone is slowly moving outward. In a few 100 million years, Earth might be too close to the Sun, approaching the inner edge of the habitable zone. In about 1 billion years, increased solar luminosity might trigger a runaway greenhouse effect like what happened on Venus. But this is far in the future, and life on Earth has plenty of time before the Sun's brightening becomes a problem. In fact, other factors like the eventual exhaustion of carbon dioxide due to continued plate tectonics might become limiting factors before the Sun's brightening does. For other stars, the habitable zone is different depending on the star's luminosity. More luminous stars have habitable zones farther out. Less luminous stars have habitable zones closer in. Red dwarf stars, which are much less luminous than the Sun, have habitable zones very close to the star, sometimes within the orbit of Mercury. Sun-like stars have habitable zones similar to ours. More massive stars, brighter than the Sun, have habitable zones farther out. But these stars also have much shorter lifetimes. A star twice the Sun's mass might only live a few billion years before exhausting its fuel. This might not be enough time for complex life to evolve on planets around such stars. Understanding the Goldilocks zone is crucial for the search for life beyond Earth. When we discover planets around other stars, one of the first things we want to know is whether they're in the habitable zone. Are they at the right distance from their star to potentially have liquid water? This doesn't tell us whether they actually have life, but it tells us whether they're worth studying more carefully. A planet in the habitable zone is a candidate for further investigation. We want to study its atmosphere, looking for signs of water vapor, oxygen, methane, gases that might indicate biological activity. But, as we've seen with Venus and Mars, being in the habitable zone distance-wise is not enough. You also need the right atmosphere, the right size to maintain that atmosphere, a magnetic field to protect it, plate tectonics or some other mechanism to regulate climate over long timescales, and probably other factors we're still discovering. Earth is habitable not just because it's in the right place, but because of a fortunate combination of many characteristics working together. This might make truly Earth-like planets rare in the galaxy, or it might mean habitable planets come in varieties we haven't imagined yet, with different combinations of factors creating habitability through different means. As we continue exploring, we're finding that the Goldilocks zone concept is more complex than we initially thought. It's not just about distance from the star. It's about the interplay between star type, planet size, atmospheric composition, magnetic field, geological activity, and probably other factors we don't fully understand yet. But the fundamental principle remains true. There's a region around every star where conditions could potentially support liquid water on a planet's surface, and liquid water remains our best guess for what's necessary for life to arise and thrive. The Goldilocks zone is where we should focus our search for life beyond Earth. It's where we might find other worlds that, like Earth, are just right. Let's dig deeper into why the inverse square law matters so much for planetary habitability, because this is one of those physics concepts that sounds abstract but has profound real-world implications. Imagine the sun as a point source radiating energy in all directions. That energy spreads out as it travels away from the sun, like ripples spreading on a pond when you drop a stone. At any given distance from the sun, that energy is spread across a sphere. The surface area of a sphere is 4 pi r squared, where r is the radius, the distance from the center. As you go farther out or increases, so the surface area increases with the square of the distance. Since the total amount of energy passing through each sphere is the same, it just came from the sun and spread out. The energy per unit area decreases as the area increases. This means if you're at 1 AU from the sun, you get a certain amount of energy per square meter. If you move to 2 AU, you're twice as far, but the sphere's surface area is 4 times larger, so each square meter receives 1/4 as much energy. At 3 AU, each square meter receives 1/9 as much energy. This rapid drop-off with distance is why the habitable zone is so narrow. A small change in distance creates a large change in energy received, which creates a large change in temperature. Let's quantify this more precisely for the planets in our solar system. Mercury at 0.39 AU receives about 690 watts per square meter more than Earth. Venus at 0.72 AU receives about 1,240 watts more than Earth. Mars at 1.52 AU receives about 770 watts less than Earth. Jupiter at 5.2 AU receives only about 50 watts per square meter, less than 4% of what Earth receives. Saturn at 9.5 AU receives only about 15 watts per square meter. These outer planets are clearly far outside any reasonable definition of the habitable zone. They're so cold that even with thick atmospheres providing greenhouse warming, they can't maintain liquid water on any hypothetical surface. But wait, Jupiter and Saturn don't have solid surfaces. They're gas giants, mostly hydrogen and helium. What about their moons? Could any of Jupiter's or Saturn's moons be in a habitable zone even though they're far from the Sun? This is where things get interesting. It turns out there are other types of habitable zones beyond just the traditional distance from star definition. Some moons of the outer planets might have liquid water not on their surfaces, but underneath ice shells, heated not by the sun, but by tidal forces. Europa, one of Jupiter's large moons, is a prime example. Europa is covered in a layer of water ice, but below that ice, scientists think there's a global ocean of liquid water, maybe 100 kilometers deep. How can this be when Europa is so far from the Sun? The answer is tidal heating. Europa orbits Jupiter in an elliptical orbit. As it moves closer to and farther from Jupiter, Jupiter's gravity squeezes and stretches Europa. This constant flexing generates friction inside Europa, which generates heat. This tidal heating, combined with some residual heat from Europa's formation and radioactive decay in its rocky interior, is enough to maintain liquid water beneath the ice shell. Europa might be habitable, not on its surface, but in that subsurface ocean. This is a completely different kind of habitable zone. It's not about distance from the Sun, it's about tidal heating from a giant planet. Saturn's moon, Enceladus, has a similar situation. It has geysers at its south pole, shooting water ice and vapor into space. This material is coming from a subsurface ocean heated by tidal forces from Saturn. The Cassini spacecraft flew through these geysers and detected organic molecules, salts, and other materials that suggest a potentially habitable ocean beneath Enceladus's surface. So, when we think about habitable zones, we need to think beyond just the traditional circumstellar habitable zone, the Goldilocks zone around a star. There are other possibilities. Tidal heating can create habitable environments. Radioactive decay in a planet's interior can provide warmth. Even a very thick atmosphere on a planet far from its star could trap enough heat through an extreme greenhouse effect to maintain liquid water. The universe might have many ways of creating conditions suitable for life, and we're only beginning to understand them. But let's return to the traditional Goldilocks zone and think more carefully about what determines its boundaries. The inner edge of the habitable zone is set by the runaway greenhouse effect we saw on Venus. If a planet receives too much solar radiation, water evaporates into the atmosphere. Water vapor is a greenhouse gas. More water vapor means more greenhouse warming, which causes more evaporation. This positive feedback loop can lead to a runaway effect where all the water evaporates and is eventually lost to space. The inner edge of the habitable zone is defined as the distance where this runaway greenhouse effect becomes inevitable for an Earth-like planet. For the Sun, this is estimated to be around 0.95 AU, just inside Earth's current orbit. This is uncomfortably close. Some scientists have suggested Earth might already be near the inner edge, and as the Sun continues to brighten, we might face a runaway greenhouse in the future. Other scientists think Earth is more securely in the denged, habitable zone and won't face this problem for at least another billion years. The uncertainty comes from the complexity of Earth's climate system and the role of clouds, which can either warm or cool the planet depending on their altitude and type. The outer edge of the habitable zone is set by the limit of the greenhouse effect. Even with a thick atmosphere of carbon dioxide, there's a point where a planet is so far from its star that it simply can't trap enough heat to keep water liquid. Carbon dioxide itself starts to condense out of the atmosphere at very cold temperatures, forming clouds or even precipitating as dry ice snow. Once carbon dioxide starts condensing, you lose your greenhouse warming and the planet becomes even colder. This sets a maximum distance for the habitable zone. For the Sun, the outer edge is estimated around 1.37 AU, which is between Earth and Mars, but closer to Mars. Mars is just outside this boundary at 1.52 AU. If Mars had a thick carbon dioxide atmosphere and no other complications, it might just barely be able to maintain liquid water on its surface. But Mars is also small, which affected its ability to hold onto a thick atmosphere, so it's not a perfect test case. Between these boundaries, roughly from 0.95 to 1.37 AU for the Sun, conditions allow liquid water to exist on a planet's surface, assuming the planet has an appropriate atmosphere. The exact boundaries depend on assumptions about atmospheric composition, cloud cover, and other factors, so different researchers calculate slightly different numbers. But the general range is clear. Earth sits comfortably in the middle of this range, which is why we have abundant liquid water and why life evolved here. Now let's think about how atmospheric composition affects temperature and habitability in more detail. We've mentioned greenhouse gases several times, but let's really understand what's happening. When sunlight reaches a planet, some is reflected back to space by clouds, ice, and the surface. The rest is absorbed, warming the surface. The warm surface radiates energy back out. But this outgoing radiation is in the infrared part of the spectrum, longer wavelengths than visible light. Greenhouse gases in the atmosphere, particularly carbon dioxide, water vapor, and methane, absorb this infrared radiation. They don't absorb all of it, but they absorb significant amounts at specific wavelengths. When a greenhouse gas molecule absorbs an infrared photon, it gains energy and becomes excited. Shortly after, it re-emits a photon, releasing that energy. But the re-emitted photon goes in a random direction. Some go back down toward the surface, Some go sideways, some go up towards space. On average, about half the absorbed energy is re-emitted downward. This is the greenhouse effect. Energy that would have escaped to space is redirected back toward the surface, warming it further. The more greenhouse, our gases in the atmosphere, the stronger this effect. With no greenhouse gases at all, Earth's average temperature would be about -18 degrees Celsius, well below freezing. With current levels of greenhouse gases, average temperature is about 15 degrees Celsius, a warming of 33 degrees. This natural greenhouse effect is essential for life as we know it. Without it, Earth's oceans would freeze. But too much greenhouse effect, like on Venus, creates uninhabitable conditions. The key is balance. Earth has maintained this balance through the geological carbon cycle we mentioned earlier and through biological processes. Plants and photosynthetic bacteria remove carbon dioxide from the atmosphere during photosynthesis, converting it to organic matter and releasing oxygen. When these organisms die and get buried, some of that carbon is locked away in sediments and eventually becomes fossil fuels. Animals and decomposers release carbon dioxide back through respiration and decomposition. The ocean absorbs carbon dioxide from the atmosphere, and marine organisms use it to build shells and skeletons, which eventually form limestone on the ocean floor. All these processes regulate atmospheric carbon dioxide levels. For most of Earth's history, this regulation has kept carbon dioxide in a range that maintains habitable temperatures. There have been excursions, periods when Earth was much warmer or much colder than today. During snowball Earth events, most or all of Earth's surface froze over, possibly multiple times in the distant past. During the Cretaceous period with the dinosaurs, Earth was much warmer than today, with no ice at the poles and higher sea levels. But these variations stayed within bounds that allowed liquid water and life to persist somewhere on the planet. Human activities are now perturbing this system by burning fossil fuels and releasing carbon dioxide that had been locked away for millions of years. Atmospheric carbon dioxide has increased from about 280 parts per million before the Industrial Revolution to over 420 parts per million today. This is causing global average temperatures to rise, though we're still well within the habitable range. Earth is not going to become Venus, but the rate of change is rapid compared to natural variations, and it's affecting climate, ecosystems, and human societies. This brings up an important point. The Goldilocks zone tells us where liquid water can exist, but it doesn't tell us where life will arise or where life will thrive indefinitely. A planet can start out habitable and become uninhabitable through internal processes like volcanic activity changing the atmosphere, or through external processes like changes in the star's output or impacts from asteroids. Conversely, our planet might start out marginal and become more habitable through the evolution of life itself. Life on Earth has profoundly affected our atmosphere. The oxygen in our atmosphere is almost entirely the result of photosynthesis by cyanobacteria and plants. Early Earth had virtually no free oxygen. Life created the oxygen-rich atmosphere we breathe today. So, habitability is not a static condition determined solely by a planet's position in space. It's a dynamic condition influenced by geology, biology, stellar evolution, and chance events. The Goldilocks zone gives us a starting point for understanding where habitability is possible, but the full story is much more complex. Let's also think about the time dimension. The habitable zone moves over time as stars evolve. Stars like the Sun gradually increase in luminosity over billions of years due to changes in their internal structure as they fuse hydrogen into helium. The Sun has increased in brightness by about 30% since it formed 4.6 billion years ago. This means the habitable zone has been moving slowly outward. Early in Earth's history, Earth received less solar radiation than today. Yet, we know liquid water existed on Earth at least 3.8 billion years ago, possibly even earlier. How was Earth warm enough? The answer is that early Earth's atmosphere had much higher concentrations of greenhouse gases, particularly carbon dioxide and possibly methane. These gases provided enough greenhouse warming to compensate for the dimmer sun. As the sun brightened over time, the geological carbon cycle gradually removed carbon dioxide from the atmosphere through weathering and carbonate formation, preventing Earth from overheating. This is often called the faint young sun paradox, and its resolution demonstrates the importance of atmospheric regulation in maintaining habitability over geological timescales. Looking forward, the sun will continue to brighten. In about 1 billion years, it might be bright enough that even with reduced atmospheric carbon dioxide, Earth's oceans will start to evaporate. The increased water vapor will enhance the greenhouse effect, leading toward a runaway greenhouse scenario similar to what happened on Venus. In about 5 billion years, the sun will exhaust its hydrogen fuel and begin evolving into a red giant, expanding enormously and likely engulfing the inner planets, including Earth. So, Earth's long-term habitability has limits set by stellar evolution. We have about 1 billion years left in the habitable zone before things start getting uncomfortably hot, though that's still a vast amount of time by human standards. For planets around other types of stars, the timescales are different. Smaller red dwarf stars burn their fuel very slowly and can live for tens or even hundreds of billions of years, much longer than the current age of the universe. Planets around red dwarfs could potentially remain habitable for extremely long periods if other factors don't intervene. Larger stars burn through their fuel quickly. A star twice the Sun's mass might only live a few billion years before exhausting its hydrogen. This might not be enough time for intelligent life to evolve, if the time it took on Earth is any guide. So, the type of star matters for long-term habitability. The width of the habitable zone also depends on star type. Luminous stars have wider habitable zones in absolute terms, covering more physical distance, but they're also farther from the star. Dim red dwarfs have narrow habitable zones close to the star. A planet in the habitable zone of a red dwarf might orbit in a matter of days or weeks rather than the 1 year Earth takes to orbit the Sun. This close proximity creates additional complications. The planet might become tidally locked, always showing the same face to its star, like the Moon always shows the same face to Earth. This could create extreme temperature differences between the permanent day side and permanent night side, though a thick atmosphere might redistribute heat and moderate these differences. Close-in planets around red dwarfs also experience strong tidal forces that can cause internal heating, similar to what we see in Europa. This tidal heating could help keep the planet warm, extending the habitable zone outward. But these planets also face intense stellar activity. Red dwarfs often have powerful flares that release huge amounts of radiation and charged particles. These flares could strip away a planet's atmosphere over time unless the planet has a strong magnetic field for protection. So, planets around red dwarfs face a different set of challenges for maintaining habitability compared to planets around sun-like stars. Understanding all these factors is crucial as we search for life beyond our solar system. We've discovered thousands of exoplanets, planets orbiting other stars, and many of them are in their star's habitable zone. But being in the habitable zone doesn't mean they're Earth-like or habitable in practice. We need to study their atmospheres, their sizes, their stars' properties, and many other factors to assess whether they could actually support life. This is one of the main goals of current and future space telescopes. The James Webb Space Telescope, for example, can analyze the atmospheres of some exoplanets, looking for water vapor, carbon dioxide, oxygen, methane, and other gases that might indicate habitable conditions or even life itself. We're at the beginning of a new era in understanding habitable worlds beyond Earth. The Goldilocks zone concept guides our search, telling us where to look. But we're also learning that habitability might be more diverse than we imagined, with different types of planets achieving it through different means. Subsurface oceans on icy moons, planets with thick hydrogen atmospheres that provide extreme greenhouse warming, planets around red dwarfs with strong tidal heating. The universe might be full of habitable environments, each unique, each with its own story. And somewhere out there, in one of these Goldilocks zones around one of the hundreds of billions of stars in our galaxy, there might be another world where beings are looking up at their sky and wondering, just as we are, whether they're alone. But the Goldilocks zone isn't just an astronomical concept. It's also a profound reminder of how special and fragile our situation is. We live on a planet that happens to orbit at just the right distance from a star of just the right type, with just the right atmosphere, just the right size, just the right magnetic field, just the right moon stabilizing our tilt, just the right plate tectonics regulating our climate. Change any one of these factors significantly, and Earth might not be habitable. We won the cosmic lottery, not once, but many times over, in many different ways. Think about how unlikely this combination is. Stars form from collapsing gas clouds. Planets form from the disk of material surrounding young stars. This process is random and chaotic. Planets end up at various distances from their star through our combination of where they formed and how they migrated over time. Some planets form beyond the frost line, where it's cold enough for ice to condense, then migrate inward, becoming hot Jupiters orbiting very close to their stars. Other planets form closer in and stay there. The exact location depends on countless factors, the mass of the protoplanetary disk, the presence of other planets, gravitational interactions, the timing of formation relative to the dissipation of the gas disk. That Earth ended up at 1 AU from the Sun, right in the middle of the habitable zone, is fortunate. But it's not guaranteed. Most planetary systems don't have planets in the habitable zone, or if they do, those planets might not have the other characteristics needed for habitability. Finding Earth-like planets around Sun-like stars in the habitable zone is one of the main goals of exoplanet research, and early results suggest such planets might not be extremely rare, but they're not common either. We're still working out the statistics as we discover more and more planets. And even if a planet is in the right place, it needs the right size. Too small and it can't hold an atmosphere, or it cools too quickly and loses its magnetic field like Mars did. Too large, and it might become a mini Neptune with a thick hydrogen atmosphere that's very different from Earth's. There seems to be a range of sizes, roughly from about half Earth's radius to about twice Earth's radius, where rocky planets can maintain Earth-like atmospheres and surface conditions. Within this range, the details depend on composition, formation history, and other factors. The planet also needs the right composition. Rocky planets in the inner solar system are made mostly of silicon, oxygen, iron, magnesium, and other heavy elements. Gas giants farther out are mostly hydrogen and helium because that's what was available in the cooler outer regions of the protoplanetary disk. A rocky planet needs to form in the right region, with the right building blocks. It needs enough water, delivered perhaps by comets or asteroids from the outer solar system, to have oceans, but not so much that the entire surface is covered in a deep global ocean with no land. Earth's surface is about 70% ocean and 30% land. This balance might be important for the geological carbon cycle and for the evolution of complex life. The star itself needs to be the right type. Too massive, and it lives too briefly for complex life to evolve. Too small, and the habitable zone is so close that planets face tidal locking and strong stellar activity. Sun-like stars, those with masses between about 80% and 120% of the Sun's mass, seem to offer the best conditions. They live long enough for life to evolve, billions of years. Their habitable zones are at comfortable distances where planets don't face extreme tidal effects. They're relatively stable without the intense flaring activity of smaller, red dwarfs, but even within this range, there's variation. Some stars are more active than others. Some have higher metallicity, more heavy elements which affects planet formation. The Sun is fairly typical of its type, which is probably good for our habitability. And then there are all the historical contingencies. Earth might have been hit by a Mars-sized object early in its history, an impact that ejected material that formed the Moon. Without this impact, Earth might not have a large moon stabilizing its tilt. Earth might have experienced different amounts of volcanism, different patterns of plate tectonics, different asteroid impacts delivering water or causing mass extinctions. Each of these events shaped Earth's history and its path toward habitability. Change the details, and you might get a very different outcome. So, when we think about the Goldilocks zone, we should remember it's just one factor among many. It's necessary for habitability as we understand it, but it's far from sufficient. Earth is habitable because of a fortunate combination of many factors, some determined by physics and chemistry, others by chance events in our planet's history. This makes Earth precious. We're not just living on any planet. We're living on a world that's exactly suited for life, that has maintained those conditions for billions of years, that allowed life to arise and evolve into the incredible diversity we see today, including us. This also gives us perspective on our responsibility. We're stewards of a rare and precious world. Earth might be one of very few planets in the galaxy that's truly Earth-like, with abundant liquid water, a thick but not too thick atmosphere, a protective magnetic field, stable climate regulation, and billions of years of habitability ahead. We should take care of it. The choices we make about our environment, our climate, our ecosystems matter not just for us, but for all the life that shares this planet with us. We're part of an unbroken chain of life stretching back nearly 4 billion years. All of it possible because Earth sits in the Goldilocks zone and has the right characteristics to maintain habitable conditions. And as we search for life elsewhere, as we discover more exoplanets and characterize their properties, we should remember that the Goldilocks zone gives us a starting point, a framework for understanding where habitability is most likely. It focuses our search on the most promising targets, the planets orbiting at the right distance from their stars. But we're also learning that the story is more complex than just distance alone. Let's explore all the other factors that determine whether a planet in the Goldilocks zone is actually habitable. The type of star matters enormously. We've mentioned this briefly, but let's really understand why. Stars come in different masses, different sizes, different temperatures, different luminosities. Astronomers classify them using spectral types, letters that indicate temperature. From hottest to coolest, the main types are O, B, A, F, G, K, and M. Our Sun is a G-type star, specifically G2. It's yellow, medium temperature, medium mass, medium luminosity, fairly average in most respects, which is probably fortunate for life. The most massive stars, O and B types, are incredibly hot and luminous. They burn their fuel so quickly that they only live a few million to a few tens of millions of years before exhausting their hydrogen and exploding as supernovae. This is far too short for complex life to evolve, if Earth is any guide. It took billions of years for intelligent life to appear on Earth. These massive stars are dead long before that could happen on any planets orbiting them. So, despite having habitable zones, and they do, very far from the star due to their high luminosity, O and B stars are not good candidates for hosting life. A-type stars are slightly cooler and less massive, living perhaps a billion years or so. This is getting into the realm where simple life might arise, but probably not enough time for complex multicellular life, and certainly not intelligent life. F-type stars are cooler still and live a few billion years, approaching the time span we see on Earth. These might be viable, though we're not sure whether a few billion years is enough. Earth had simple, single-celled life for most of its history. Complex multicellular life only appeared in the last 600 million years or so. Intelligence is even more recent. If this timeline is typical, F-type stars might be marginal. G-type stars like the Sun live about 10 billion years. Our Sun is currently about 4.6 billion years old, not quite halfway through its main sequence lifetime. This long lifetime gave life on Earth plenty of time to evolve from simple chemistry to single cells to complex organisms to intelligence. G-type stars seem ideal for life. K-type stars are slightly cooler and less massive than the Sun, and they live even longer, perhaps 15 to 30 billion years. These could be excellent candidates for hosting life. Their habitable zones are closer to the star than ours, but not so close as to create major problems. Then we get to M-type stars, the red dwarfs. These are by far the most common type of star in the galaxy, making up about 70 to 80% of all stars. They're small, cool, dim, and incredibly long-lived. A red dwarf with half the Sun's mass might live 50 billion years. One with a third the Sun's mass could live 100 billion years or more. That's longer than the current age of the universe. These stars will keep shining long after stars like the Sun have died. From a longevity standpoint, red dwarfs seem perfect for life. There's plenty of time for evolution to work, but red dwarfs have complications. Their habitable zones are very close to the star because they're so dim. A planet in the habitable zone of a red dwarf might orbit at a distance similar to Mercury's orbit, around the Sun, or even closer. At these close distances, tidal forces from the star are strong. Over time, these forces slow the planet's rotation until it becomes tidally locked, always showing the same face to the star. The Moon is tidally locked to Earth, which is why we always see the same side. A tidally locked planet around a red dwarf would have one side in permanent day, the other in permanent night. This creates extreme conditions. The day side could be scorching hot while the night side is freezing cold. Any atmosphere would try to flow from hot to cold, potentially freezing out on the night side. If too much atmosphere condenses on the night side, the planet loses its greenhouse effect and gets even colder. Some models suggest this could lead to atmospheric collapse, where the entire atmosphere freezes out. Other models suggest a thick enough atmosphere could redistribute heat from day to night side, keeping both at moderate temperatures. We're not sure which is correct. It probably depends on the specifics of the planet and its atmosphere. Red dwarfs are also very active, especially when young. They have powerful magnetic fields that generate enormous flares, sudden releases of energy that can be much more powerful relative to the star's output than solar flares. A large flare from a red dwarf could temporarily double or triple the star's brightness and release intense ultraviolet and X-ray radiation. For a planet in the close-in habitable zone, this radiation would be intense. It could strip away the planet's atmosphere over time, especially if the planet doesn't have a strong magnetic field for protection. Red dwarfs also take a long time to settle down. Young red dwarfs can be extremely active for hundreds of millions or even billions of years. During this time, any planets in the habitable zone are being battered by radiation and stellar wind. This might prevent life from arising or sterilize any life that does arise. Only after the star settles into a quieter old age would conditions become favorable. But then you have the benefits of that extremely long lifetime. If life can survive the turbulent youth or arise after the star calms down, it has tens or hundreds of billions of years to evolve. Red dwarfs are a mixed bag for habitability. They're common and long-lived, but they present unique challenges. So star type matters. For the best chances of finding Earth-like life, we probably want to look at type stars like the Sun and K-type stars that are slightly cooler. These stars are stable, long-lived, and their habitable zones are at comfortable distances. F-type stars might work too. Red dwarfs are worth investigating despite their challenges because they're so numerous. If even a small fraction of red dwarf planets are habitable, there could be billions of habitable worlds around red dwarfs in our galaxy alone. Now let's talk about atmospheric composition in more detail, because this is absolutely critical for habitability. We've discussed how greenhouse gases warm a planet, but let's think about what makes a good atmosphere for life. You need the right pressure. Too thin and liquid water is unstable. Too thick and you get crushing surface pressure and extreme greenhouse warming like Venus. Earth's atmosphere at sea level has a pressure of about 1 bar, 1 atmosphere. This is the baseline we use. Surface pressures anywhere from maybe half a bar to a few bars could probably support life. Much thinner and water doesn't stay liquid. Much thicker and you run into problems. You need the right composition. Earth's atmosphere is mostly nitrogen and oxygen with trace gases. The nitrogen is largely inert, providing bulk but not reacting much. The oxygen is reactive but maintained at steady levels by photosynthesis from plants and cyanobacteria. Before photosynthesis evolved, Earth's atmosphere had almost no free oxygen. Early life evolved in an oxygen-free environment. Only after cyanobacteria invented photosynthesis did oxygen levels rise, eventually reaching current levels of about 21%. This is high enough to support combustion and animal respiration, but not so high that everything spontaneously catches fire. Carbon dioxide is a trace gas today, about 0.04%, but it's crucial for the greenhouse effect. Without it, Earth would be much colder. With too much, Earth would be much hotter. The amount of carbon dioxide is regulated over geological timescales by the carbon cycle we discussed. Water vapor is also a greenhouse gas, and its amount in the atmosphere depends on temperature. Warmer temperatures mean more evaporation, more water vapor, more greenhouse warming. This is a positive feedback, but it's limited by the fact that water vapor condenses as clouds and rain. The atmosphere can only hold so much water vapor before it precipitates out. An atmosphere also needs to be thick enough to provide substantial greenhouse warming, but transparent enough to let sunlight through. If an atmosphere absorbs too much visible light, the surface doesn't get enough energy from the star. This is a problem for planets with very thick atmospheres dominated by certain gases. The balance is delicate. You want greenhouse gases that absorb outgoing infrared radiation but don't absorb incoming visible light. Carbon dioxide, water vapor, and methane do this well. They're transparent to visible light but opaque to infrared. For life as we know it, having liquid water is essential, but having oxygen is not. Early Earth had no free oxygen and was still habitable for anaerobic life, life that doesn't need oxygen. Oxygen only became abundant after photosynthesis evolved. But oxygen is useful for complex multicellular life. Cells with oxygen metabolism can extract much more energy from food than anaerobic cells. This is why anaerobic organisms tend to be small and simple, while aerobic organisms can grow large and complex. So, a planet with an oxygen-rich atmosphere would be more promising for complex life, though oxygen would likely be a biosignature itself, evidence of photosynthetic life. One intriguing idea is that we might detect oxygen in the atmosphere of an exoplanet and infer the presence of life. Oxygen is reactive. It combines with rocks, with organic matter, with many other substances. It doesn't persist in an atmosphere unless something is constantly replenishing it. On Earth, that something is photosynthesis. Plants and cyanobacteria split water molecules, releasing oxygen. If photosynthesis stopped, atmospheric oxygen would gradually decrease over millions of years as it reacted with surface materials. So, finding oxygen in an exoplanet's atmosphere, especially in combination with water vapor and carbon dioxide, would be strong evidence of biological activity. But we have to be careful. There are abiotic processes, non-biological processes that can produce oxygen. Ultraviolet light from the star can split water molecules in the upper atmosphere, releasing oxygen. However, this process also releases hydrogen, which escapes to space. Without a continuous supply of water, this can't produce large amounts of oxygen. A planet with lots of water continually being split by UV light might accumulate some oxygen even without life, though probably not as much as Earth has. We'd need to look at the full atmospheric composition and consider the star's properties to distinguish biological from abiotic oxygen. Methane is another interesting gas. On Earth, most methane is produced by biological processes, particularly by microbes in wetlands and in the guts of animals. Methane in the presence of oxygen is unstable. They react to form carbon dioxide and water. So finding methane and oxygen together in an atmosphere would be very interesting. They shouldn't coexist unless something is continuously producing both. On Earth, photosynthesis produces oxygen and microbial life produces methane. The combination is a strong biosignature. Abiotic processes can produce methane, volcanic activity for example, but typically not in large amounts and not in the presence of oxygen. The James Webb Space Telescope is capable of detecting some of these gases in the atmospheres of certain exoplanets, particularly those that transit their stars, passing in front of them from our perspective. During a transit, starlight passes through the planet's atmosphere before reaching us. Different gases absorb light at specific wavelengths, creating absorption features in the spectrum. By carefully analyzing these spectra, we can determine what gases are present and in what amounts. This is one of the most exciting capabilities of JWST. We're finally able to study exoplanet atmospheres in detail and search for signs of habitability or even life. Now let's talk about magnetic fields, because these are crucial for protecting atmospheres from being stripped away by stellar wind. A magnetic field is generated by moving electrically conductive material. In Earth's case, convection in the liquid outer core, molten iron moving in circulation patterns, generates electric currents. These currents create a magnetic field that extends far into space, forming the magnetosphere. The magnetosphere deflects charged particles from the solar wind, preventing them from hitting the atmosphere directly. Without a magnetic field, a planet is vulnerable. The solar wind, a stream of charged particles from the sun, can interact directly with the upper atmosphere. These particles can knock atoms and molecules out of the atmosphere, slowly stripping it away. Over millions or billions of years, a planet without a magnetic field can lose a significant fraction of its atmosphere, especially lighter gases like hydrogen and helium. Mars is a prime example. Mars had a magnetic field early in its history, but lost it as the planet cooled and its dynamo shut down. Without magnetic protection, Mars's atmosphere was gradually stripped away by the solar wind, thinning from perhaps a thickness comparable to Earth's to the thin atmosphere we see today. Earth maintains its magnetic field because our interior is still hot enough to keep the outer core liquid and convecting. This requires a large enough planet with enough internal heat. Smaller planets cool faster and lose their magnetic field sooner. Larger planets stay warm longer and can maintain magnetic fields for billions of years. So, planet size matters for habitability, not just for holding atmosphere through gravity, but also for generating a protective magnetic field. There are other ways to generate magnetic fields. Jupiter, a gas giant, has an extremely strong magnetic field generated by convection in metallic hydrogen deep in its interior. Some exoplanets might have liquid water oceans containing dissolved salts. If these oceans are deep and convecting, they might generate weak magnetic fields, though probably not as strong as what you'd get from a molten iron core. The point is, having some source of magnetic field is important for long-term atmospheric retention, especially for planets around active stars like red dwarfs that produce strong stellar winds and frequent flares. Interestingly, Venus has no significant magnetic field. Its core might be entirely solid, or it might not be convecting for some reason. Despite this, Venus has retained an extremely thick atmosphere. How? Venus's thick atmosphere itself provides some protection. The upper atmosphere ionizes from solar radiation, and this ionized gas interacts with the solar wind, deflecting it. It's not as effective as a true magnetic field, but it's enough to prevent rapid atmospheric loss. Venus also started with so much atmosphere that even billions of years of slow loss hasn't removed it all. This shows that magnetic fields are helpful but not absolutely required if a planet has other protective mechanisms. Now, let's discuss the Moon's role in Earth's habitability, because this is fascinating and often overlooked. Earth's moon is unusually large compared to the planet. Most moons in the solar system are tiny compared to their planets. The exceptions are the large moons of the gas giants, but even those are small compared to their host planets when you consider the mass ratio. Earth's moon has about 1/4 Earth's diameter and about 1/81st Earth's mass. It's relatively huge. This large moon affects Earth in several important ways. First, The moon creates tides. The moon's gravity pulls on Earth, creating bulges in the oceans and even slight deformations in the solid Earth itself. As Earth rotates, these bulges move around the planet, creating the rise and fall of ocean tides we experience daily. Tides are important for coastal ecosystems. They create intertidal zones where conditions alternate between wet and dry, submerged and exposed. These zones might have been important for the evolution of early life, providing environments where organisms could adapt to varying conditions. Some scientists speculate that tidal pools might have been sites where life first emerged, or where life made the transition from water to land. Second, the moon stabilizes Earth's axial tilt. Earth's rotation axis is tilted about 23.5 degrees relative to its orbital plane. This tilt creates our seasons. As Earth orbits the Sun, different hemispheres receive more direct sunlight at different times of year. Without the moon, Earth's tilt would vary chaotically over millions of years due to gravitational perturbations from other planets, especially Jupiter. Computer simulations show that without the moon, Earth's tilt could vary from nearly 0 degrees, no tilt, no seasons, to perhaps 80 degrees or more, extreme tilt, extreme seasons. These variations would happen over timescales of millions of years, creating wild swings in climate. With the moon's gravitational influence, Earth's tilt is stabilized. It varies by only about 1 degree over tens of thousands of years, a tiny variation that contributes to ice age cycles but doesn't create catastrophic climate change. This stability has allowed Earth's climate to remain relatively predictable over the long term, which probably helped complex life evolve. Organisms can adapt to slow climate changes, but rapid swings might be too much. The moon is slowly moving away from Earth. Tidal interactions transfer angular momentum from Earth's rotation to the moon's orbit. This slows Earth's rotation, making days longer and pushes the moon farther away. Early in Earth's history, days were much shorter, perhaps only 6 hours, and the moon was much closer, perhaps half its current distance. Over billions of years, Earth's day has lengthened to its current 24 hours, and the moon has receded to its current distance of about 384,000 kilometers. This process continues today. The moon is currently receding at about 3.8 centimeters per year, and Earth's day is lengthening by about 2 milliseconds per century. Eventually, in the far future, this process will reach an equilibrium where Earth and Moon are mutually tidally locked, each always showing the same face to the other. At that point, Earth's day will equal the Moon's orbital period, about 47 current days. This is billions of years in the future, so it's not something we need to worry about. But it shows that the Earth-Moon system is dynamic, constantly evolving through tidal interactions. Not all planets have large moons. Venus has no moon at all. Mars has 2 tiny moons, Phobos and Deimos, each only a few kilometers across, probably captured asteroids. Mercury has no moon. The gas giants have many moons, but they're small relative to the planets. Earth is unusual in having such a large moon, and this might be another factor that makes Earth particularly well suited for life. We don't know how common large moons are around terrestrial planets in other star systems, but it's something to consider when evaluating exoplanet habitability. Speaking of exoplanets, let's explore some of the actual planets we've discovered in the habitable zones of other stars, because these are the targets where we're most likely to find life beyond Earth. As of the mid-2020s, we've discovered thousands of exoplanets, and many of them orbit in their star's habitable zone. Let me highlight a few particularly interesting examples. The TRAPPIST-1 system is one of the most famous. TRAPPIST-1 is a red dwarf star about 40 light-years from Earth. It has 7 known planets, all roughly Earth-sized, and 3 of them orbit in the habitable zone. This is extraordinary. Most stars have 0 planets in the habitable zone. TRAPPIST-1 has 3. The planets are designated TRAPPIST-1e, F, and G. Planet E receives about the same amount of stellar energy as Earth does from the Sun. Planet F receives less, similar to Mars. Planet G receives even less. All 3 could potentially have liquid water if they have appropriate atmospheres. The TRAPPIST-1 planets are also remarkably compact. All 7 planets orbit closer to their star than Mercury orbits the Sun. But remember, TRAPPIST-1 is a cool, dim red dwarf, so being close doesn't mean being too hot. The planets are likely tidally locked, always showing the same face to the star. Whether they have atmospheres and whether those atmospheres can maintain habitable conditions is still unknown. JWST has started observing these planets, measuring their atmospheres if they exist. Early results suggest at least some of them might lack thick atmospheres, which would be disappointing for habitability. But the observations are still ongoing. We might yet find that 1 or more TRAPPIST-1 planets is habitable. Proxima Centauri b is another intriguing case. Proxima Centauri is the closest star to the Sun, only about 4.2 light-years away. It's a red dwarf, smaller and cooler than TRAPPIST-1. In 2016, astronomers discovered a planet orbiting Proxima Centauri at a distance that places it in the habitable zone. The planet Proxima Centauri b has a mass at least 1.3 times Earth's and receives about 2/3 the stellar energy Earth receives. If it has an atmosphere, it could have liquid water on its surface. But Proxima Centauri is an active star with frequent flares. In 2017, a massive flare increased the star's brightness by 1,000 times for several seconds. Such flares would bathe the planet in intense radiation. Whether life could survive such conditions is debatable. Perhaps life could exist in subsurface environments protected from the radiation. Or perhaps the planet has no atmosphere anymore, stripped away by the flares and stellar wind. We're trying to learn more about Proxima b, but it's challenging, because even though Proxima Centauri is the nearest star, it's still over 4 light-years away. Kepler 180f was one of the first Earth-sized planets discovered in a habitable zone. It orbits a red dwarf about 500 light-years away. It's about 10% larger than Earth and receives about 1/3 the stellar energy Earth receives, similar to Mars, but around a cooler star. If it has a thick atmosphere with greenhouse warming, it could be habitable. We know almost nothing else about it, no information on its atmosphere or surface conditions. It's too far away for detailed study with current technology, but it's an existence proof that Earth-sized planets in habitable zones are out there. Kepler 452b orbits a G-type star, the same type as the Sun, making it one of the most Earth-like planets known in terms of star type. The star is slightly larger and older than the Sun, and the planet orbits at a similar distance to Earth, just inside the outer edge of the habitable zone. It's about 60% larger than Earth, so it's sometimes called a super-Earth. We don't know if it's rocky or has a thick atmosphere or what its surface conditions are. It's about 1,400 light-years away, too far for detailed atmospheric studies. But it's the kind of planet we're looking for, similar size to Earth, orbiting a Sun-like star in the habitable zone. There are dozens more examples. LHS 40b, a super-Earth around a red dwarf that might be an ocean world. TOI 700d, an Earth-sized planet in the habitable zone of a red dwarf. Kepler 442b, another super-Earth in a habitable zone. Each of these is a potential site for life. Each is a world where liquid water might exist, where the conditions might be right for biology to emerge and thrive. We don't know which, if any, of these planets actually has life. We might not know for decades or longer, but the fact that they exist, that there are many planets in habitable zones, gives us hope that life might be common in the universe. The search for life is one of the great scientific quests of our time. For all of human history, until the last few decades, we could only wonder whether other worlds existed. Now we know they do. Thousands of them, and many are in habitable zones. The next question is whether any of them has life. To answer that, we need to study their atmospheres in detail, looking for biosignatures, gases or combinations of gases that indicate biological activity. This is what JWST and future telescopes will do. It's a long process. Each planet requires many hours of observation to gather enough light to analyze its atmosphere, and atmospheric signals are weak and subtle. But we're making progress. Let's also consider that life might be more flexible than we imagine. We've focused on liquid water and Earth-like conditions because that's what we know. But life on Earth exists in extreme environments we once thought impossible. There are organisms living in boiling hot springs at temperatures above 90 degrees Celsius. There are organisms in frozen Antarctic lakes at Dainiti, temperatures well below zero. There are organisms kilometers underground in solid rock, living off chemical energy from minerals. There are organisms in the deep ocean at hydrothermal vents where superheated water spews from the sea floor, living in complete darkness using chemical energy from sulfur compounds. These extremophiles show that life can adapt to conditions far outside what we consider normal. Maybe life exists on planets we'd consider marginal, just outside the traditional habitable zone. Maybe life exists in subsurface oceans, on icy moons like Europa or Enceladus, warmed by tidal heating rather than sunlight. Maybe life exists in the clouds of Venus, floating in a layer where temperature and pressure are moderate despite the hellish surface conditions below. Maybe life exists on rogue planets, worlds ejected from their star systems, wandering through interstellar space, kept warm by internal heat from radioactive decay. We're broadening our definition of habitability as we learn more. The traditional habitable zone is still the best place to look, but it's not the only place. Life might be more common and more diverse than we imagine. Every environment on Earth that has liquid water has life. Every single one, from freezing cold to boiling hot, from the deepest ocean to the highest atmosphere, from the driest deserts to the wettest rainforests. Wherever there's liquid water, there's life. This suggests life is opportunistic, arising wherever conditions permit and adapting to whatever environment it finds itself in. If this is true universally, if life arises wherever it can and adapts to local conditions, then the universe might be teeming with life in forms we haven't imagined. The Goldilocks zone tells us where life most like Earth's might exist. But life unlike Earth's might exist almost anywhere. Under the ice of Europa, in the atmosphere of a hot Jupiter, on a planet around a red dwarf with no oxygen but plenty of methane and ammonia. In subsurface aquifers on Mars. Life might be everywhere, just not always in forms we recognize or can easily detect. This is both exciting and humbling. Exciting because it means we have many places to search and many chances to find life. Humbling because it reminds us how limited our perspective is. We only know one example of life, Earth life. It's carbon-based, uses water as a solvent, requires certain ranges of temperature and pressure, uses DNA to store information. But maybe life elsewhere uses different chemistry, different solvents, different information storage. Maybe there are forms of life so different from Earth life that we wouldn't recognize them even if we saw them. Science fiction has imagined many exotic forms of life. Silicon-based life using silicon instead of carbon. Life in liquid methane on Titan using completely different chemistry than Earth. Life that exists as electromagnetic patterns in stellar atmospheres. These are speculative, but they remind us to keep an open mind. The universe is vast and has had billions of years for evolution to experiment. The diversity of life might be beyond our current imagination. But for now, our search focuses on Earth-like life because that's what we know how to look for. We search for liquid water. We search for oxygen and methane as biosignatures. We focus on planets in habitable zones around sun-like stars. This is a practical approach. We can't search everywhere at once. We have to prioritize. The Goldilocks zone is the highest priority because it's where conditions most resemble Earth, where we have the best chance of finding life we'd recognize, and even finding microbial life elsewhere would be profound. It would answer one of the biggest questions in science. Are we alone? Is life unique to Earth, or is it common in the universe? Finding even simple microbes on Mars or Europa or an exoplanet would tell us life arises naturally when conditions are right. It would suggest the universe is full of life, that we're part of a biological cosmos, not isolated on one special planet. This would change how we see ourselves and our place in the universe. Finding intelligent life would be even more profound. We've been searching for signals from alien civilizations for decades using radio telescopes, listening for intentional broadcasts or accidental radio leakage from technological civilizations. So far, we've found nothing. Either intelligent life is rare, or it doesn't broadcast, or it uses communication methods we haven't thought of, or we haven't looked in the right place at the right time yet. But we keep searching because the implications of contact would be enormous. Imagine receiving a signal from another civilization. Imagine learning we're not alone, that intelligence has arisen elsewhere, that there are other beings who look up at the stars and wonder and explore and try to understand. It would be the most important discovery in human history. It would unite humanity in ways nothing else could. Our differences would seem trivial compared to what we share, our common origin as life on Earth, our common existence as intelligent beings in a vast cosmos. But even if we never find intelligent life, even if we only ever find microbes or no life at all beyond Earth, the search itself is valuable. It teaches us about planets and stars and atmospheres and chemistry and biology. It pushes our technology forward as we develop better telescopes and instruments. It inspires young people to study science and pursue careers in research. It reminds us of our place in the universe, tiny but curious, brief but capable of understanding cosmic truths. The Goldilocks zone is where this search begins. It's the region around every star where life as we know it could exist. It's defined by temperature, by the possibility of liquid water, by distance from the star. But, as we've seen tonight, habitability depends on much more than just distance. Star type, planet size, atmospheric composition, magnetic field, geological activity, moons, asteroid impacts, countless factors determine whether a planet in the habitable zone is actually habitable in practice. Earth is habitable because everything came together just right. The right star, the right distance, the right size, the right atmosphere, the right moon, the right geological processes. We're incredibly fortunate, and we're incredibly rare. There might be billions of planets in our galaxy, but how many are truly Earth-like? How many have all the factors that made Earth not just habitable but sustainably habitable for billions of years? We don't know yet, but we're beginning to find out. Every exoplanet we discover, every atmosphere we analyze, every habitable zone planet we characterize, brings us closer to answering the big questions. How common is life? How special is Earth? Are we alone? The Goldilocks zone guides our search, telling us where to look first, where the conditions are most promising. And as we search, we learn more about our own planet, our own habitability, our own cosmic context. We are children of the Goldilocks zone. Life arose here because Earth sits at the right distance from the Sun with the right conditions. Every living thing, every species, every ecosystem, every human civilization, all of it exists because of this one simple fact. We're in the right place. The place that's not too hot, not too cold, but just right. And that makes all the difference. Think about what we've learned tonight and what it means for humanity's future. We're at a turning point in history. For the first time, we can actually search for life beyond Earth in a systematic, scientific way. We have the technology to detect exoplanets. We can measure their sizes, their masses, their orbital distances. We can determine whether they're in the habitable zone, and now, with JWST and future telescopes, we can study their atmospheres, looking for the chemical signatures that might indicate life. This is extraordinary. Just a few decades ago, we didn't know whether planets existed around other stars at all. It was reasonable to wonder whether planetary systems were rare, whether our solar system was unusual. Now we know planets are common. Nearly every star has planets, and many of those planets are in habitable zones. The universe is full of worlds. The question now is not whether habitable worlds exist, but whether life has taken hold on any of them. The implications go beyond just scientific curiosity. Understanding habitability helps us understand our own planet better. Earth is our only home, the only habitable world we can reach with current technology. The nearest potentially habitable exoplanet is over 4 light years away. With our fastest spacecraft, it would take tens of thousands of years to get there. We're not leaving Earth anytime soon. This makes Earth precious beyond measure. It's the only habitable world we've got. Climate change, driven by human activities, is altering Earth's habitability. We're increasing atmospheric carbon dioxide, warming the planet, changing precipitation patterns, melting ice, raising sea levels. These changes happen slowly by human timescales, but rapidly by geological timescales. We're conducting an uncontrolled experiment with our planet's climate system. Understanding the Goldilocks zone and planetary habitability gives us perspective on what we're doing. We see what happened to Venus with its runaway greenhouse effect. We see what happened to Mars when it lost its atmosphere. These are cautionary tales. Earth won't become Venus. We can't release enough carbon dioxide to match Venus's atmosphere. But we can make Earth less habitable for human civilization and for many species. We can disrupt agriculture, flood coastal cities, trigger mass extinctions. The Goldilocks zone tells us Earth's habitability isn't guaranteed forever. It depends on maintaining the right atmospheric composition, the right temperature range, the right balance of factors. We have the power to disrupt that balance. We also have the power to protect it. Studying exoplanets and habitability also prepares us for humanity's long-term future. Someday, perhaps centuries or millennia from now, we might develop technology that allows travel to other star systems. If we do, we'll want to know where to go. Which stars have habitable planets? Which systems are most Earth-like? The search we're conducting now, cataloging exoplanets and characterizing their properties, is creating a map of potentially habitable worlds. Future explorers might use this map to choose destinations. Or perhaps we'll never leave the solar system physically, but we'll send robotic probes to study nearby stars and their planets. Even at a fraction of light speed, probes could reach Proxima Centauri in decades. They could study Proxima Centauri B up close, landing on its surface if it has one, analyzing its atmosphere and geology, searching for life. They could send data back to Earth, expanding our knowledge of habitable worlds. This kind of exploration might happen within this century if we make it a priority. There's also the possibility of communication rather than travel. If intelligent civilizations exist on planets in other stars' habitable zones, We might detect their radio or optical signals, or they might detect ours. Humans have been broadcasting radio signals into space for about a century now, since the invention of radio. Those signals have spread out in a sphere about 100 light-years in radius. Any civilization within that sphere could potentially detect our signals if they're listening. And we're listening for their signals with projects like SETI, the search for extraterrestrial intelligence. Communication across interstellar distances would be slow. A signal to Proxima Centauri takes about 4 years to arrive. A reply takes another 4 years to return. That's an 8-year round trip for a single exchange. For more distant stars, the delays are even longer. A signal to a star 100 light-years away takes a century to arrive. Whoever sent it would be long dead before any reply arrived. But civilizations might send messages anyway, knowing that future generations would receive replies. Or they might send extensive information, libraries of their knowledge and culture, not expecting a conversation but offering their story to anyone who listens. Imagine receiving such a message. Imagine learning about another civilization, their history, their science, their art, their philosophy. It would transform our understanding of life and intelligence in the universe. It would show us that the path from chemistry to biology to intelligence to civilization can happen elsewhere, that Earth's story isn't unique. This would be profound. Even if we never meet face to face, even if we only ever exchange messages across light years, it would change everything. But even without finding other intelligent life, the search for any life beyond Earth is worthwhile. Finding microbes on Mars or Europa would tell us life arises naturally when conditions are right. If life arose independently on 2 worlds in our own solar system, it suggests life is common throughout the universe. We'd infer that most planets in habitable zones probably have life, at least simple microbial life. The universe would be biological, not just physical. Life would be a natural part of cosmic evolution, emerging wherever chemistry and energy and liquid water come together. This would still leave questions. How often does life become complex? How often does intelligence emerge? These might be much rarer transitions than the origin of life itself. Earth had microbial life for billions of years before complex multicellular organisms evolved. Intelligence arose only in the last few million years, very recently on cosmic timescales. Maybe most life in the universe is microbial. Maybe intelligence is incredibly rare. Or maybe the transition to complexity and intelligence is inevitable, given enough time, and the universe is full of civilizations. We just haven't found each other yet. These are the questions that keep astrobiologists awake at night. They're questions we might answer in our lifetimes if we're fortunate, or they might remain mysteries for generations to come. But we're asking them, and that itself is remarkable. We're using our intelligence to understand our cosmic context, to search for our place among the stars, to look for kindred spirits in the universe. This is what makes us human. Our curiosity, our drive to explore and understand, our refusal to accept ignorance when knowledge is possible. The Goldilocks zone is more than just a scientific concept. It's a symbol of our search for meaning in the cosmos. It represents the idea that there are places out there, distant worlds orbiting distant stars, where conditions might be just right for life, where the story of evolution might be unfolding just as it did here, where perhaps intelligence has arisen and civilizations have formed and beings are looking up at their sky, wondering about the universe just as we do. We are united with these hypothetical beings, if they exist, by our shared existence in Goldilocks zones. We're all children of habitable worlds, products of billions of years of evolution in environments that were just right for life. We're all made of the same elements, forged in stars and scattered through space, assembled into planets orbiting in temperate zones where chemistry can become biology. We're all asking the same questions. Where did we come from? Are we alone? What is our purpose in this vast universe? These questions transcend species, transcend worlds, transcend the vast distances between stars. They're universal questions that any intelligent beings anywhere would ask, and the Goldilocks zone is where beings capable of asking these questions arise. It's where habitable worlds exist, where life can begin and evolve and eventually look up at the stars with wonder and curiosity. So, when you think about the Goldilocks zone, remember, it's not just about temperature and liquid water and distance from a star. It's about possibility. The possibility of life, of intelligence, of civilizations, of connection across the cosmic void. It's about hope that we're not alone. And it's about responsibility to preserve the one habitable world we know we have, Earth, the planet that's just right. We started this journey by asking why Earth is special, why life exists here and not everywhere else. The answer is the Goldilocks zone. Earth sits at the right distance from the sun to have liquid water, but that's just the beginning. Earth also has the right size to hold an atmosphere and maintain geological activity, the right atmosphere to provide greenhouse warming without becoming too hot, the right magnetic field to protect that atmosphere from the solar wind, the right moon to stabilize our axial tilt, the right plate tectonics to regulate carbon dioxide over geological timescales. All these factors working together make Earth not just habitable, but sustainably habitable for billions of years. This combination might be rare, or it might be more common than we think. We're only beginning to understand how many Earth-like worlds exist. Every year, we discover more exoplanets in habitable zones. Every year, we refine our understanding of what makes a world habitable. The picture becomes clearer, slowly, piece by piece, observation by observation. And each observation brings us closer to answering the fundamental question: are we alone? Whether we find life elsewhere or not, whether we find intelligence or only microbes or nothing at all, the search itself enriches us. It expands our perspective. It reminds us that Earth, for all its beauty and diversity, is just one world among countless billions. We're part of something much larger than ourselves, much larger than our species, much larger than our planet. We're part of a cosmic story that began with the Big Bang and continues through the formation of stars and planets and the emergence of life and intelligence. We're part of the universe understanding itself. The Goldilocks zone is where this understanding happens. It's where life can arise and persist and eventually evolve to the point where it looks outward and asks why. It's where chemistry becomes biology, where biology becomes consciousness, where consciousness becomes curiosity. It's where beings like us appear, able to wonder and explore and imagine. And it's where, perhaps, we'll someday make contact with others who did the same on their own worlds, orbiting their own stars in their own Goldilocks zones. Until that day, if it ever comes, we continue our search. We build better telescopes, we discover more planets, we study more atmospheres, we refine our understanding of habitability, we look for biosignatures, we listen for signals, we reach out hoping someone reaches back, and in the process, we learn about ourselves, our planet, our place in the cosmos. We learn what makes Earth special and what we must do to keep it that way. The Goldilocks zone shows us that habitability is delicate. It requires the right conditions, maintained over long periods, balanced precisely. Change too much and you lose it. Venus and Mars show us what happens when that balance is lost. Earth shows us what's possible when everything aligns just right. We're the beneficiaries of cosmic good fortune, living on a world that won the habitability lottery. Our responsibility is to recognize that fortune and preserve it for future generations. To be good stewards of the one habitable world we're certain exists. And as we search the stars for other habitable worlds, as we expand our understanding of where life might exist, we carry with us the knowledge gained from our own Goldilocks zone. We know what to look for. We know what matters. Distance from the star, yes, but also star type, planet size, atmospheric composition, magnetic field, geological activity. All these pieces of the habitability puzzle. Each piece we understand better helps us identify which distant worlds might harbor life. Someday, perhaps soon, perhaps generations from now, we'll make a discovery that changes everything. We'll find a planet with oxygen and methane in its atmosphere, clear signs of life. Or we'll detect a radio signal from another civilization, or we'll land a probe on Europa and find microbes swimming in its subsurface ocean. That discovery, when it comes, will be one of the greatest moments in human history. It will answer a question as old as civilization. Are we alone? But even before that discovery, even now as we search, we're already learning the answer to another question. Is Earth special? Yes, not because it's the only habitable world, there might be many, but because it's ours, because it's where we evolved, where our story unfolds, where everything we know and love exists. Earth is special because it's the one habitable world we can touch and see and protect. It's the pale blue dot, as Carl Sagan called it, the only home we've ever known. The Goldilocks zone reminds us how fortunate we are to live here, in this perfect place, not too hot, not too cold, but just right. It reminds us to cherish what we have and to search with open minds and hopeful hearts for others who might share our good fortune on their own worlds, in their own Goldilocks zones around their own stars. The universe is vast, full of stars and planets and possibilities, and somewhere in that vastness, in one of those zones where conditions are just right, there's us, looking up, wondering, searching, hoping. That's the beauty of the Goldilocks zone. It's where hope lives, where life is possible, where we find our place among the stars. And perhaps that's the most important lesson from understanding the Goldilocks zone. It teaches us both humility and wonder. Humility because we see how special and rare our situation might be, how fortunate we are to exist on this one world where everything came together just right. Wonder because we realize the universe is full of potential, full of places where the same story might unfold, where life might arise and evolve and look outward with the same questions we ask. We stand at a unique moment in history. We're the first generation that can search for life beyond Earth systematically. We're the first to know that planets orbit other stars. We're the first to study exoplanet atmospheres. We're the first who might, in our lifetimes, discover evidence of life elsewhere. That's extraordinary. That's something our ancestors could only dream about. And we're doing it. We're living through it. This is our generation's great exploration, our contribution to humanity's ongoing quest to understand our place in the cosmos. The Goldilocks zone guides that quest. It tells us where to look, what to prioritize, which worlds deserve our closest attention. It's the framework that organizes our search, the concept that makes the vast universe feel slightly less overwhelming. Somewhere in that immensity, there are zones around stars where conditions are just right. And in those zones, maybe, just maybe, we're not alone. Thank you for joining me on this journey through the habitable universe. If you found this exploration valuable, a like or subscribe really helps the channel keep making these deep explorations of space. And remember, every time you look up at the stars, some of those points of light are stars with planets orbiting in their habitable zones. Worlds where the temperature might be just right for liquid water. Worlds where life might exist. Worlds where perhaps beings are looking back at our sun, wondering if anyone is here, just as we wonder about them. We live in a universe full of possibilities, and the Goldilocks zone is where those possibilities are most likely to become reality. Good night, and may you never forget how special our place in the cosmos truly is.